All right, guys. Sorry that we didn't get to everything we wanted to get to in class today, but let's talk about the imaginary numbers and the complex numbers. So we discussed how the complex numbers were the combination of the real numbers, everything you've worked with to this point, and this imaginary number set, this new number set. I believe we discussed in class the reason this number set was created was because mathematicians wanted an answer to deal with the square root, or technically any even root, of a negative number, which does not exist in the real numbers. Like your calculator tells you, error, non-real answer. So in creating this imaginary number set, they allowed for what we call the complex numbers. And we discussed this in second period and eighth period. We'll just go over this really quickly here. A is a real number. B is technically a real number, but because B is being multiplied as the coefficient factor with I, this term is actually an imaginary term, or we call the whole thing an imaginary number. And that should be plus or minus, right? So we could have a real number plus an imaginary number, or a real number minus an imaginary number, and those would be complex numbers. The important thing to understand is what I is. I is not a variable. I is actually the square root of -1. Now, the square root of -1 doesn't exist in the reals. That's the reason it's I. If there's an I attached to your number, it's an imaginary term. It's an imaginary number. Now, the catch is I squared is actually a real number, because if we take the exponent of power of 2 of a root of 2, those cancel, leaving me with a real number, -1. And that's going to become important when we're simplifying I squared later. So how do we deal with this? Well, when we think about the square root of -4, what we can do is we can actually factor -4 to the factors -1 times 4. We talked about in algebra that there's a property which, if we're multiplying under the radical, we can actually split that radical over the multiplication into the multiplication of two separate radicals. So this becomes the square root of -1 times the square root of +4. Well, the square root of -1 becomes the number I, and the square root of 4 becomes 2. Right? And so what we have here is that the square root of -4 is actually 2i. Now you might say, well, that's cheating. Well, that's what the mathematicians did, and that's why we have the imaginary numbers. Now, the good news is we're going to work with our imaginary numbers almost identically to how we worked with variables. The only exception to that is when we have an imaginary number to an exponent greater than 1, we have to simplify this, and we'll look at an example of that. All right, so let's look at adding and subtracting complex or imaginary numbers here. The good news is, like terms, if you have the same type of term, then you're good to go. So you have a real number 1 and a real number 5, and you're adding, so 1 plus 5 is 6. I have an imaginary term, 2i, an imaginary term, -3i. I add them up, 2 plus -3 gives me -i, and that is what we would get there. Same deal here. Now we're subtracting, so you might want to use our trick of changing the signs in the second number and change it to addition. But -3 plus -7 is -10. -5 plus -3i is -8i. So this is exactly the same thing we'd be doing if there was a variable like x or y there. So here, the -4 is the only real number here, so -4 is just going to stay what it is, and -4i and 5i would combine to give me just +i. So that's adding and subtracting complex numbers, whether it's just I, whether it's whether we have a real number there, that's all we're doing. Okay, let's turn to the second page here, and let's look at multiplication of our numbers. Right, again, we're going to do the same exact thing. If this was a 2x instead of a 2i, what would we do? We would just distribute. We would distribute. 3 times 5 is 15. 5 times -2i is -10i. And we are done. All right, over here it gets a little trickier. Now we're multiplying an I, now we're distributing an imaginary term there. So 2 times 4 is 8, and we leave the I. 2 times 3 is 6, and I times I is I squared. Now this is where we've got to be careful, because I squared actually simplifies to, as we saw right here, -1. So, sorry if you're getting nauseous, I apologize. Right, so this actually becomes 8i plus 6 times -1. So we would write this as the real number first, negative 6 plus 8i. Right? Same deal on 10. You are not, and I'm not even going to say the F word. I'm not even going to say it. You're distributing. So 5 times 2, 5 times 2i, 3i times 2, 3i times negative 2. So I'll get 10 minus 10i, and then I will get 6i minus 6i squared. Right, so now we need to combine our like terms here, but we also need to simplify that I squared. So this becomes 10 minus 4i minus 6 times negative 1. Well, 6 times negative 1 is now a real number, positive 6. So I can combine my like terms one more time to get 16 with the real numbers, and 16 plus 4i. Once again, distribute. Negative 4, distribute the I, I'll get negative 24 plus 28i, I will have 6i plus 7i squared. Right, so I combine my like terms there, negative 24 plus 34i, change the I squared to a negative 1, simplify that, that's negative 7, so then I have negative 24 plus 34i minus 7, combine my like terms, negative 31 plus 34i. All right, so that's adding, subtracting, and multiplying with our complex and imaginary numbers. Again, other than simplifying the I squared here to negative 1, everything's identical to what we did with variables. Now, what happens when the exponent of I is greater than 2? So what we want to do is figure out how many times we can pull an I squared out of this number. So I to the 9th can be written as I squared times I squared times I squared times I squared times I to the 1st. I'm using my exponent property in reverse. So instead of adding all the exponents to simplify to one exponent, I'm breaking that one exponent down into multiple factors of the same base here. Now we know, we talked about I squared is negative 1, this I squared is negative 1, this I squared is negative 1, this I squared is negative 1, and I to the 1st is just I. Well, if I multiply negative 1 times negative 1 times negative 1 times negative 1, all of these negative 1s multiplied together simplify to just 1 I, or we can just write it as I. So I to the 9th will simplify to positive I, right? Well, what about I to the 12th? Well, I can write this, I can change this to I squared 6 times, right? Because 6 to 12 divided by 2 is 6. So that is essentially negative 1 to the 6th. Negative 1 to the 6th is going to be positive 1, and so we are good. All right, same deal. Now here, it's a little trick here. How many times can I get I squared in there? Well, it doesn't divide into 31 evenly, but if I go down 1 to an even number, I can think of this as I to the 30th times I to the 1st. All right, now this here, we could write this as, oops, sorry, wrong, I squared 15 times. Well, that's really the same thing as negative 1 multiplied by itself 15 times. And that, if you do that, that's an odd number, so that's going to come out as negative 1. So what we'll end up with here is negative I. Last one here, 54. All right, so I can write this as I squared 28 times, right, because half of 54 is not 28. How about 27 times? I squared is actually negative 1, and negative 1 multiplied by itself 27 times, because 27 is odd, will simplify to just negative 1. All right, when you simplify the imaginary number with an exponent that's greater than 1, you will always end up with one of these 4 answers as your simplified expression. Positive I, negative I, positive 1, or negative 1. All right, now in 16 through 18 here, we're going to be doing the same thing we did over here with negative 4. We're going to be simplifying this, right? And the key is we first have to separate my factors, the negative 1 away from the 81. Then I can split my radical here, using my radical property, the square root of -1 becomes I. The square root of 89 is 9. So the square root of -81 is 9I. Same deal here. Going to follow the same procedure. Now, do I need to see all of these steps every single time? No, I don't need to do that. I would hope you could all get this down to I square root of 40 without needing to show me this work, but I'm just writing it all out so you can see that. Now here's the catch though. Square root of 40 is not simplified. The I is simplified, and that's hanging outside the radical, but the square root of 40 is not simplified. Depending on how you learned it in algebra, the square root of 40, we want to break that down into its prime factorization. So the way I showed it last year was we break 40 into 4 times 10. We can do 2 times 2 and 2 times 5. And if I write this, it's 2 to the 3rd times 5. Right now, since I have a root of 2, what I'm looking for is squareds here. So I can write this as 2 squared times 2 times 5 underneath that radical. So I can write this as I times the square root of 2 squared times 2 times 5. I can again break this up. Well, I don't want to, sorry, I'm not actually going to break up this last one. I want to break this 2 squared off. So it's I times the square root of 2 squared times the square root of 2 times 5. And the reason I want to do that is because my exponent of 2 can cancel my radical. So this becomes I times 2. And then since I can't do anything with the 2 and the 5, we'll simplify them back to the square root of 10. And my final answer here is 2I square root of 10. All right, there's a lot going on in that example there. It's simplifying the square root of 40 is its own beast. So if simplifying the square root of 40, if all of this work here is something we need to talk about, please make sure you ask a question. All right, last one here. Let's work with the square root of -20 first off to the side here. So square root of -20 becomes the square root of -1 times the square root of 20, which is I times the square root of 20. Now we can break the square root of 20 down. 2 times 10, 2 times 2, and you can see I have 2 squared. So this can become I times 2 squared times 5. I can break this down into I times 2 squared times the square root of 5, right? Those exponents cancel. I'm left with 2I square root of 5. So now I'm going to come back up and I'm going to replace 2 square root of 5 with 2I square root of 5 over 2 replaces the -20. Now I have 2 terms on top and a term on the bottom, so I can divide out, cancel a 2 out of all of them, and that will leave me with 3 plus or minus I square root of 5. All right, again, the I is actually probably easier than the simplifying of our radicals here. So if everything I did with the square root of 20 here is a complete mystery to you, please bring it to class. We'll talk about it. Please come get some help outside of class because that is a skill from algebra we do expect you to have in being able to simplify square roots that are not perfect squares. All right, well, sorry, this went a little longer than I thought. You have the ability to fast forward or skip ahead whenever you would like, but I worked out all of the examples in the notes here. So please try the homework and come to class with questions tomorrow. We'll see you then.